Hey guys, my name is Vidisky for Nogorawan, and today I'll try to explain to you about binary heap. It's not a very difficult concept and it's fairly easier compared to like other data structure I've explained before. So let's just get started. It won't be long. I trust you guys. So again, what is a binary heap? It is a complete binary tree, meaning that it's filled from top to bottom except maybe the bottom right part. So you'll see what I'm trying to talk about. Unlike self-balancing trees, there are no particular relationships among the nodes, only parent-child relationship depending on the type of the tree. So, other tree might have other kind of relationship with its sibling. For instance, the sibling is greater than the other siblings, the right sibling is greater than the left siblings, and so on and so forth. But then in binary heap, the only relationship you can get is the top-down relationship between the parents and the children, and it always depends on these two things, whether the types of heap is a max heap or a min heap. So in a max heap, we can see that here in a max heap, between the parent and the parent will always be greater than the child. Here, parent greater than the child, parent greater than the child, parent greater than the child. However, there are no clear relationship between the siblings and maybe the uncle and so on and so forth. But then this 26 is lower than 19. It's on the lower level. However, you can be assured that 26 here will always be lower than 33. So there's only a parent-child relationship in a max heap. And in min heap, it's the opposite. The parent is always less than the child, so it can be assured. And here again, there are no exact relationship between the siblings and the uncle and the particular node and so on and so forth. So what else? Although the diagram of this data structure is commonly represented as a tree, as I have shown you before, its implementation uses array data structure. So I actually tried to create a tree using a tree implementation, and it's practically significantly more difficult compared to like using an array data structure. And why? Why array? It provides easy access to the parent and children. Because it is a complete tree, it's easy to like create the array representation of the tree. Comparison to creating the array itself, in comparison to creating a tree data structure to represent this heap tree. Aside from that, heap sort is always performed to array. So we have algorithm for heap sort already for arrays, and if you learned array before, you might already learn heap sort, and this is just a data structure to represent that particular array. So let's see the array implementation of this particular data structure. Start root at array 1 and store nodes left to right. What does it mean? What does it mean? So here we have this root here, particular root here, and it will be kept not in array 0 here. There are no array 0 because it will mess up with the formula. But instead, I will place this particular node in array number 1. I'm using red. I'll change it to white. So, and store nodes left to right. So in left here we have 42 and right here we have 35. It's always top down, left, right. What does it mean, top down, left, right? It starts with the highest level and it starts with the leftmost node. So we have 42, right? And then we have beside 42 we have 35, and because we ran out of node, we need to go deeper to the lower level of the tree. So next is 33, then 31 to the right of it again. We don't go to the child of 33 or so, but then we jump to 19, the rightmost, the right of the 9. At the right of 19 we have 27, and because we ran out of nodes, we go deeper. We have 10, 26, and 14. This is what I meant by top, down, left, right. So as you might have seen, how to implement this in tree, it's fairly difficult because we do not have clear relationship between the particular node and the uncle. So that's why we cannot easily access this 19 over here if we want to insert another node. So that's the array implementation. I will link down the Java implementation of Heap Tree in the description below, and let's move on. So let's try with insertion. We will try to insert 5, 23, 13, 14, and 17. In heap tree, we always try to compare the parent and the child every time we do an operation to maintain the rules of the heap tree. So first, we'll start with the node, right? 5 here and the root node, and we will place in the real implementation, we will place the 5 in this particular array, array 1, not array 0, because it will mess with the formula, and I'll explain to you about the formula after this. I should have explained it before, but I'll explain it now. So next 23. Oh, we don't start with because like in BST, binary search tree, we will place 23 because it's bigger than 5 at the right hand of the node. No, in heap tree we always start top down, left, right. So it's 23 here. That is why there is no clear relationship between the siblings, but only the relationship between the parents and the node. And we will check whether 5 and 23 follows the rule. Let's make this a max heap, alright? So I will check whether 5 is greater than 23, and it's not. That is why I will need to exchange the position of 5 and 23 here. So 23 will be on top and 5 here. Next, since it is okay, I will try to insert 13, and according to the rule, top, down, left, right. So we'll fill here 13, and I'll check, not with the sibling, but with the parent. Is 23 greater than 13? Because it is greater, that is why I'll let it be. Now, 40. Where should we place 40? Because top, down, left, right. Remember, top, down, left, right. 40 will be here. Okay, something's wrong with this tree? Yes, because 5 is no greater than 40. That is why I'll need to exchange 5 with 40 here. So, 5 with 40 here. 5 and 40, and we do this recursion wise until we get the root node, and we check, is 23 greater than 40? No, that's why you also exchange the position of 23 and 40. I deleted that one. So it's 23 and 40, and we check with the well, we don't need to check because it's assured that 30 will always be less than 23. But then we got this root node here already, right? So since it's a root, we stop, and it still follows the rule. And 17, is it here? No, it's top, down, left, right, guys? So we need to fill this first 17 and check whether it violates the rule. 17 is less than 23, and it is a heap tree. And as you see here, this is what you mean by complete tree. We complete everything from top, down, left, right. We only have an empty node here, a null node here, right? And here, null node. So this is what you mean by a complete tree. It's totally filled on all level, and there's only a difference of one level between the complete level and the incomplete level. And you see, we always fill the left part here, and so on and so forth. And so what's the array implementation of this is actually I kind of forgot to like fill in the array, but yeah, it's 40, 23, 13, we jump here 5 and 17. So what's this relationship of this particular node that is represented in an array? So if we have an array X, for instance, array X will always have the left node. Let's say the index of array X is I. The left child of X will always have the index of 2i, while the right part of the right child of the node will always have the index of 2i plus 1. It's always assured, and that's why we do not insert 0 in the index 0, because it will mess with the rule. And let's check. For instance, I have array X of 23 is in index 2, and I want to check what's the left child and the right child of index 2. Left child of index 2 is 2 times 2, which is 4, plus no plus anything, right? 2 times 2 is 4. So it says that the left child of index 2 is index 4, and it is correct, right? 23 has a left child of 5. And what's the right child? 2 times 2 plus 1, which is 5. Index 5, 17. Again, correct. Right child of index 2 is 17, which is in index 5. So that's the particular rule. So remember, left child is 2i or 2x if you may, and the right child is 2x plus 1. And if you want to check the parent relationship, we can use inverse function, right? So for instance, we have y is equal to 2x, meaning that the left child of index x is the 2 times the index of x, right? But what's the inverse of this function? The index of the function, if you is basic math, it's x is equal to y over 2. And we replace the position of y and x in an inverse function. It results to y is equal to x over 2. So for instance, I have index 4 here. The parent of index 4 will be x over 2, which is index 2. Let's check with the right node. Y is, let's delete erase all. So I have the right child, which is which has the formula of y is equal to 2x plus 1. I will do the inverse of this. Y minus 1 is equal to 2x, and x is equal to y minus 1 over 2. Do the inverse, meaning that we substitute y and x here. Y is equal to x minus 1 divided by 2. And if we check, damn, but we remember that the relationship is here, here and here, right? The left, right, and parent. So if I want to check the right node, what's the parent of the right node? 5 minus 1, 4 divided by 2, 2. So the parent is 2, so it's proven. So this a bit of math here. We can use this for our implementation and so on and so forth. Now, what about deletion? It's fairly simple. In deletion, there's one rule. In deletion, when you delete the particular node, usually, and most of the time, it's always the highest or lowest level, meaning the root of the max heap or the mean heap, meaning that we want to delete 40 over here. Let's say delete 40, right? We always replace it with the end of the array, meaning it's since this is like 40, 23, I actually number this 13, 5, and 17. If I delete 40, I will replace this with the end of the array, which is 17. So I'll need to keep track of the tail of the array, right? So I will replace here 17, just delete this. But after that, I will need to check with either child whether 17 is greater or less than the child, right? So I check it with the left first. 17 is less than the child, meaning that I need to switch the position of 17 and 23 here. So I'll need to exchange the position of 17 and 23 here, and 23 here becomes 17, and 17 here becomes 23. Again, I will check whether 17 is greater than 5, which it is. So this is our final result for our deletion of 40, right? And we check 23 is greater than 13, 23 is greater than 17, 17 is greater than 5. And this all follows the rule of the heap tree. So that's it. Fairly simple, right? Compared to our lessons before. And these are the resources I used and here, particularly this is a good website to like visualize the heap tree. So I'll put all the resources in the description below. And I guess that's it. Easy lesson for today, right? So yeah, peace